Hey everyone, so today we are talking about our next lesson in stoichiometry, which is limiting reactant. So today, instead of just giving you one amount of mass for a reactant, I'm going to give you two. So as you remember in our last lesson, I was saying that you have 15 grams of CH4 and O2 is in excess, right? We had too much O2. Well, now I'm going to be giving you grams of that CH4 and that O2, and you're going to have to figure out which one is in excess or which one is the limiting reactant on your own. What is the limiting reactant? Well, the limiting reactant is just the chemical that runs out first, right? If you're making hot dogs, right, they always give you more buns than hot dogs. You might have 10 hot dog buns, but only 8 hot dogs. Well, your limiting reactant is the hot dogs, okay? It's the one that is going to run out first. The same thing with chemical reactions, right? Usually when you combust something, the thing that runs out first is the gasoline, right? There's always enough oxygen in order to make the combustion happen, but there's just not enough of the hydrocarbons, enough of that gasoline, or enough coal to keep the reaction going. Okay, so that's what we're going to be talking about today, and it's just one more extra step. It's not anything too crazy. It's the same process we did last time. It's just, like I said, one more extra step. So, let's do an example. Let's say that I have C2H4 and it's going to mix with O2, and you might be saying, oh, cool, combustion reaction. You're right, okay? We have CO2 and we have H2O as our products, always for a combustion reaction. Let's go ahead and just balance this guy right off the bat, since we know that's step one of stoichiometry. So 2 here, that gives me, let's see, 4, 6, so we'll put a 3 there, and now we are balanced. Step one of stoichiometry is taken care of. It's always just good to make sure if a reaction is balanced right from the get-go. Anyway, all right, and my question is, if I have 15 grams of C2H4 and 15 grams of O2, how much CO2 is produced? Is produced. Okay, so once again, if I have 15 grams of C2H4 and 15 grams of O2, how much CO2 is produced? And now usually in previous example, I say I have 15 grams of C2H4 and 15, or an excess O2, too much O2. But now I'm not giving you that. I'm making you do an extra step. So now you got to figure out if the 15 grams of C2H4 is going to run out first, or the 15 grams of O2 is going to run out first. And a lot of times you'd like to say, oh, it's just the one that has smaller amount of grams. Here they're the same, and that doesn't actually work, because remember, it's not the grams that matters, it's the moles. So what we're going to do is we're pretty much just going to do the same step, but instead of just doing it for C2H4, we're going to do it for O2 as well. So grams to moles, mole ratio, compare that mole ratio to what we want. So let's go ahead and let's get started. So let's go ahead and start with 15 grams. Well, that marker doesn't work. Let's go ahead and start with, let's hope this guy does, there we go, 15 grams of C2H4, and let's go ahead and convert this to moles, right? That's our first step, and we'll go ahead and do that with O2 right after this. So convert this to moles. We divide by the molar mass. Carbon is 12, there's 2 of them, 24, 28 grams per mole from the 2 carbons and the 4 hydrogens. So I'm going to take 15 divided by 28 and get the limiting reactant of 0.5, pretty much 4 moles of C2H4. And I'm going to do the same for the oxygen as well. So I have 15 grams of O2, and I'm going to divide by the molar mass of O2, which is 32 grams per mole. So 15 divided by 32 is 0.4, we'll go 7 moles of O2. And now you might be saying, can we determine which one's going to run out first now? No, we can't do that now, okay? So when we're identifying the limiting reactant, we're identifying which one is smaller. We can't do that yet, okay? We got to do the mole ratio to what we want first, and then we can do it, okay? So remember, we do the mole ratio for each of these. Multiplication dot fraction bar multiplication dot fraction bar. We put what we have on bottom for C2H4. We're going to put C2H4 on bottom. For O2, we're going to put O2 on bottom. And then we got to ask ourselves, what are we trying to get? What we want on top? Well, it's asking how much CO2 is produced. So I'm going to put CO2 on top. And then remember that the numbers that go there are just our coefficients. C2H4 has a 1, CO2 has a 2 in front of it, O2 has a 3 in front of it. Okay. So now we'll solve both of these. 0.54 times 2 divided by 1 is just 1.08. So I have 1.08 moles of CO2. And then the bottom one, I'm going to take 0.47 times 2 divided by 3. And that gives me 0.31 moles of CO2. So now we can see which one is going to run out first. Which compound was our limiting reactant? Remember, it's the one that is going to run out first. It is the smaller one. All right, so we're looking at both of these, and I look at my N numbers, and the smaller one is 0.31. That's going to run out first. That's our 8 hot dogs, right? So where did that originally come from? My oxygen. My oxygen is my limiting reactant. So pretty much what you can do is you could say, this guy does not determine how much product is produced because there's too much of it. It's the excess. So you could just cross that top one out, and we're just going to focus on this bottom one now. Okay, so since O2 is our limiting reactant, I can just get rid of C2H4. I don't care about it anymore. And remember, it says how much CO2 is produced. That is typically meaning grams. So now I have 0.31 moles of CO2. Multiply it by the molar mass of CO2, which is 44. And I am going to be producing 0.31 times 44, 13.64 grams of CO2. All right, and that is it. So that's all you're doing, is that you're taking 2 grams of a compound now on your left side, both of your reactants, and you're going to see which one is going to be the limiting reactant, which one is going to be the smallest. So it just means instead of doing stoichiometry once, we just do it twice, one for each reactant, and then we figure out which one's the smallest once we get to moles of product. Let's go ahead and do another example so we make sure that we have this down. All right, so here's our next example. I didn't want to write out a huge thing. All right, I just want to say that I got this reaction up top. I got 23 grams of copper. Let's make sure that you can see that. So I got 23 grams of copper. I got 54 grams of silver nitrate. And I want to know how much silver I am going to produce. So once again here, I have 2 reactants. I didn't tell you which one I had too much of, so you got to figure it out on your own using a limiting reactant problem. Let's right off the bat, let's just check to make sure my reaction is balanced. It's not, right? I got 1 nitrate over here and 2 nitrates over here. So let's go ahead and let's balance this guy. I always do that. I might try to trick you a little bit. So make sure that you are checking to see if your equation is balanced. Now it's balanced, and now we're good to go. So again, remember, instead of just doing it for one reactant, we're doing stoichiometry for both reactants. So I'm going to start with 23 grams of copper here, and I'll put 54 grams of silver nitrate right down here. And we'll get started. I got my handy dandy periodic table so I can figure out the molar masses of these guys, right? Our second step of stoichiometry is convert whatever they give us to moles. So let's go ahead and convert both of these to moles by dividing by the molar mass. Copper's is 63.5 grams per mole. And silver nitrate, silver on its own is 108 pretty much. Nitrogen on its own is 14. And then I got 3 oxygens there, all at about 16. So I will divide by 170 grams per mole to get moles of silver nitrate. So let's go ahead and take 23 divided by 63.5. Remember, that's 63.5. And I'll get 0.36 moles of copper copper. For silver nitrate, I take 54 divided by 170, and I get 0.31. Let's just do 0.32 to keep it consistent. 0.32 moles of silver nitrate. And you might be saying, okay, which one's smaller? Not yet. We don't do that yet. Okay? We can't determine the limiting reactant because they're not in the same amount of product or whatever compound we're trying to get it to. Okay? So we can't determine limiting reactant yet. We got to do the mole ratio to what we're trying to find first, right? And what we're trying to find is silver. So remember, what we have goes on bottom. So copper on bottom for our top one. Silver nitrate on bottom for our bottom one. And what we're looking for on top, which again is silver. So Ag on top, Ag on top. For this one, it is a 2-to-1 ratio. And for silver and silver nitrate, it is a 2-to-2 ratio. So luckily for this one, it stays the same. So it's just going to be 0.32 moles of silver. And this one, I multiply by 2, right? 0.36 times 2 divided by 1 is just going to be 0.72 moles of silver. Now I can determine my limiting reactant. I have converted my moles of each of my reactants to products. Okay, so now we just got to figure out which one is smallest. A lot of times, a lot of you will pick the bigger one. Don't pick the bigger one. We pick the smaller one, the limiting reactant, the one that we have the small amount of ingredients for. Okay, so we are looking at this. Obviously, this one's the smaller one. 0.32 is a lot smaller than 0.72. So we cross this one out. And I might ask you, what was our limiting reactant? You'd say silver nitrate, right? That's where that 0.32 came from. All right, so 0.32 moles of Ag. Let's just say that I want grams of silver. Let's go ahead and let's get rid of this top one, right? We don't need it because it's in excess. It's not our limiting reactant. 0.32 moles of Ag. And if I remember correctly, the molar mass of silver is 108 grams per mole. So we'll just take 0.32 times 108, and we will produce 34.56 grams of silver. Good to know, right? Now you're kind of saying, wait, you turned 23 grams of copper into 34.56 grams of silver. Well, silver nitrate is expensive too. They take into account that there is silver in that silver nitrate, so just don't think that you're turning 23 grams of silver into 34 grams, or 23 grams of copper into 34 grams of silver. Silver nitrate is actually really expensive too. So they take into account. There's no way that you can make money on this scheme. Many people have looked into it and can't do it. Okay, so let's do one more example with limiting reactant just to make sure we really understand what our limiting reagents are. Okay, everybody, so again, I have another reaction up here, magnesium and oxygen gas, and they're going to make magnesium oxide. And it says, if I have 15 grams of magnesium and 4.2 liters of O2, how much MgO will I produce? What is the limiting reagent? First of all, reagent is the same thing as reactant. You'll just see that in some chemistry books or chemistry problems. They'll switch reactant and reagent. Same thing. In this situation, I am given 15 grams of magnesium and 4.2 liters of oxygen. Again, they give me two amounts of my reactants. They didn't tell me what the limiting reactant was. I got to figure that out on my own. And in this case, they gave me a mass and they gave me a volume. Well, we should be able to figure out how to convert those both to moles. Okay. So our stoichiometry rules, right? We got to balance our equation first. 2 oxygens, 2 oxygens. Well, now I have 2 magnesiums. Well, that's pretty easy. 2, 1, and 2. Again, they didn't tell us which one was in excess, so we got to figure out our limiting reactant on our own. So I have 15 grams of magnesium, and instead of mass for oxygen, they gave you liters of O2, which remember, we just divide by 22.4, right? We're going to assume this is at STP. So let's convert both of these to moles. We're on step 2. Magnesium's molar mass is 24.3. And remember, this isn't in grams, so we can't divide by molar mass, right? We got to divide by 22.4. We got to divide by the liters, right? Because for every 1 mole of gas at STP, it equals 22.4 liters. So that'll give us moles of each of those. So I'll take 15 divided by 24.3, and I get 0.62 moles of magnesium. Here I got 4.2 liters of oxygen. I divide by 22.4, and I get 0.1, we'll go 9 moles of O2. And you might say, limiting reactant time? No, okay? They're not in the same moles of the same type of element or compound, okay? They're different. We gotta do step 3 first, which is mole ratio. Mole ratio time. What we already have on bottom, right? Magnesium right there. Let's put magnesium on bottom, O2 on top here. We got to put O2 on bottom. And what we want on top, which is MgO, right? That's what we're trying to figure out is produced. Magnesium oxide to magnesium is a 2-to-2 ratio. And magnesium oxide to oxygen is a 2-to-1 ratio. 2-to-1 ratio. So this guy stays the same. Now we have 0.62 moles of MgO. And this one we just times by 2, right? Times 2 divided by 1, or just times by 2, is 0.38 moles of MgO. Now they're in the same compound. Now I can determine the limiting reactant. Which one is going to run out first? The smaller one, right? So when it says what is my limiting reagent, you will say O2. It is the one we have the least amount of. Not this guy. That's not our limiting reactant. Oxygen is our limiting reactant. So I'll just put that up here and put it in a little box. And now we're not done yet. We got to figure out how much MgO I produced. So I now have 0.38 moles of MgO. I multiply by the molar mass of MgO, which is 40.3. For a mass of, so we got 0.38 times 40.3, we get 15.3 essentially grams of MgO. That's it, guys. Again, it's just an extra step. We're just doing our same stoichiometry thing we've been doing, except just for one mass, you do it for 2 masses. All right? And then figure out which one's the smallest one. That's your limiting reactant. That's what determines how much of our product we produce. That's it. If you have any questions, let me know. Have yourselves